Alright, so here we are with Unit 9, Lesson 10, and we're going to get into something called acid-base titration. We will do a lab on this, and this is one of those labs I've been mentioning to you that is required but it's not required. They do ask questions on titration, so we will do a lab on this. Now, what is a titration? Basically, a titration is a process used to determine the strength, in other words, the molarity of an unknown solution. So I'll give you an example. Um, let's say we had, and this is, let's say we had a sample of an acid. Let's say we had a sample of HCl, but we didn't know how strong it was. We didn't know its molarity. Well, we could use the process of titration to determine the strength of that acid, and and this is just kind of an explanation of everything here. What we would do is we would titrate an acid and the base. The base that we would use, if we're trying to determine the molarity of an unknown acid or the molarity of an acid, we would use a base that we know the strength of, and using the machinery, the equipment that's at the bottom, we would be able to figure it out. So I think probably the easiest way, and this I think is a video, but let me go through a very quick kind of explanation here. So, and it's basically basic setup, and this is the exact same setup that we're going to use. This is a burette. This is a flask with an indicator in it, and the indicator that's generally used is phenolphthalein. And remember, phenolphthalein is colorless in an acid, and it's pink in a base. It's just a clamp here to hold this burette. Basically, the burette is kind of like a graduated cylinder, but has what's called a stopcock at the bottom, which means that you can open and close it, and the liquid that's inside the burette will drip out. And this is graduated, which means you can read how much liquid is being dispensed. So this would be 0 at the top here, and then it would go higher and higher. So for example, if it went from here to, let's say, well, this actually works out, and if the liquid moved down here, you would just measure, going again, you would just measure how much the difference is, and that would tell you how much of the acid or the base, whatever's in the burette, was dispensed. So let's give you just a quick example, and we can use the example that we had before. Let's say we don't know the molarity of our acid, and our acid that we're going to use is HCl. The base that we're going to use we'll use a simple one. We're going to use NaOH, and let's say it's 2 molar. And we're going to use, and we end up needing, let's say, 20 milliliters of the base. And the amount of acid that we used was only 10 milliliters. Well, you could plug these numbers into the equation and figure out the strength of the acid. So the molarity of the base is 2, the volume is 20, so this comes out to 40. We don't know the molarity, but we do know the base, the volume. It's 10. So how would you find this here? Well, you would simply just divide both sides by 10. It would end up being 40 over 10. So the strength of the acid would be 4. So in other words, the acid is twice as strong as the base. That's why we only needed half the amount. Now, it's a little bit more complicated than that, but basically what would happen is, in this case, you would have the base in here, and you would know the strength of the base. We said it's 2 molar. You'd have the acid in here, and in this case, you decide how much of the acid you want to use. I could use 10 milliliters, 20, I could use 100. So, and the phenolphthalein is in here. And of course, the phenolphthalein in an acid would be clear. And then you're going to let the base go drop by drop. You're going to stir this. And what's going to happen is, as soon as you reach the neutralization, the equivalence point, the end point, the solution will stay pink. That tells you now that you have now made it from colorless to slightly basic, and you've neutralized it. And then you would just read how much of this was dispensed, plug it into the formula. You already know the strength of the base that was in here. You don't know the strength of this acid, but you do know how much is in the flask because you put it in there, which is basically up to you, and you plug in the numbers. You could also do the opposite. If I had a base that I didn't know the strength of, I would put an acid in here, put the base in here, follow the same thing, and now this would be pink if I put phenolphthalein in here with a base. And as soon as it becomes clear, then you know you've reached the end point. That's the end of your experiment. You plug in the numbers, and you follow it along. Let's watch this video. I don't know how long it is, but we'll...
In a titration experiment, a solution of accurately known concentration, called a standard solution, is gradually added to another solution of unknown concentration until the chemical reaction between the two solutions is complete. Let's consider the titration of an unknown concentration of a hydrochloric acid, HCl, solution with 0.20 molar sodium hydroxide, NaOH. Click on the button to begin the titration. Choose to add NaOH to HCl in 5.00 milliliter increments. Note that hydrogen ions H plus from the acid combine with hydroxide ions OH minus from the base to produce water.
So we're adding 5 milliliters of NaOH, which is in this burette, at a time, and you'll be able to read out how much you dispense. We know the strength of the base, it's 0.2 molar, so it's very weak. We know how much HCl we started out with, and we're going to be able to figure this out, so let's keep going here. Notice the graph on the right. Now this is a little bit more detailed because in this case we're not using phenolphthalein, we're using a pH probe. Get a much more accurate reading. Notice how the pH now is going up.
At this point in the titration, the acid has completely reacted with or been neutralized by the base. This point is called the equivalence point. In the titration of a strong acid with a strong base, the pH at the equivalence point is 7. Note that only sodium ions and chloride ions are present in solution. Because these ions will not affect the pH of the solution, the pH is neutral. Click to add more sodium hydroxide.
Okay, so I think you kind of see how this is going to work. We're not going to go through the rest of it because we don't need to go past that during our lab. So once you've reached the end point, the equivalence point, then you know that your experiment is over. You would read off how much of this you use. It looks like we've used 10, 20, 30, 40. You would read off how much of this you've used. That would be the amount of NaOH you put in. You know, we started, I think, with 60 milliliters of, so that would be, so we used 30 milliliters of 0.2 molar NaOH. Our acid, we did not know the pH of, so we're going to use those numbers to plug into the equation, and you'd be set. Let's do a couple of practice problems. I'm not going to go through all of these, but you'll see here on the next page there are a couple of problems. I already kind of set them up, so let's go through them quickly. I don't want to make this video too long. So if you look at this, it says, what is the concentration of a solution of HI? So the concentration of HI, that's what it's asking you to find. So it's asking you to find the molarity of the acid. So this is our unknown. Of HI, if 0.3 liters is neutralized, so this is 0.3 liters, by 0.6 liters, that's 0.6, of 0.2 molar OH. Now if you need to slow this down and pause it and go back and look at the question, please do so. Don't just go through this if you're a little bit confused here. And then basically what you end up doing is you want to get MA by itself. So you're going to divide both sides by 0.3. So you're going to multiply 0.2 times 0.6 and then divide that by 0.3, and I believe that you get the molarity of the acid is going to be 0.4. So it's a relatively weak acid. That's question number one. I'm going to go and show you a little bit of a different thing here. Now, if you look down here at this last question, you notice I skipped 2 and 3 because I want to get to this one here. This is a little bit different, and here's why. If you look at this acid, this is an acid that's called a diprotic acid. Why is it called diprotic? That's not a term that you'll see on the Regents exam, but you need to understand that the difference between this and HCl is that this has 2 H's in it. So it's going to form twice as many H plus ions when you put it in water. So one of the things you have to add to the formula is if you have an acid that is diprotic, in addition to these two, you'd have to put a 2 in front. If it's triprotic, meaning H3, you'd have to put a 3 here. And you do the same thing for the base. If the base has more than one OH, which it doesn't here, you put that number here. Here was a 1, so we don't even really need to put it. If you had a base that had, for example, if you had this base, CaOH2, you would have to put a 2 here. Thing is, if they're both 2s, then you would just kind of ignore it because it's not going to change it. But you do have to be careful. So if you have a diprotic acid or a triprotic acid, you'd have to put either a 2 here for diprotic or a 3 for triprotic. If you have a base that has more than one OH, dihydroxy or trihydroxy, you'd have to put either a 2 or 3 here. So you really have to be careful with that. So I'm going to go through and solve this. So you're trying to get VB by itself. So you're going to divide both sides by, in essence, 1 times 0.5 is 0.5. So you're going to divide both sides by 0.5. Multiply this, so it's 2 times 1 is 2 times 50 is 100. 100 divided by 0.5, so the volume of the base is 200 milliliters. I'll give you the answer to the third one. The third one, I believe, is giving you the volume of the base is going to be, VB is going to be 20 milliliters. And the answer to the second one is the molarity of the acid is 0.625 for question number 2. So if you need to go over these, please do so in class. And we're done with this lesson.